Here we're looking at a tank that contains liquid, has a vent at the top and an outlet at the bottom through which the liquid drains. We're looking at Torricelli's law, which states that at time t seconds after the opening of the outlet, the depth of the liquid is k meters and the surface area of the liquid is a meters squared, and they're related by this differential equation here. So it's nice because in this case we've been given the differential equation. Now the k in that equation depends on different factors, including viscosity. Now, viscosity is sort of denseness or thickness of a fluid, like for example honey is very highly viscous because it's quite gooey, whereas water is not very viscous, it's quite runny. And it also depends on the cross-sectional area of the outlet, so how big this outlet is, and how much fluid it's letting out. So we're going to use Torricelli's law for this tank. It's symmetrical, it's initially full, and it has a height of 1.6 meters and a radius length of 0.4 meters. So just reading that section there, I know that when t equals 0, I know that the height of the fluid would be 1.6 meters because the entire tank is full. And we're going to use k equals 0.025, so we've been given a k constant for this particular fluid in the tank, and we need to construct an appropriate differential equation. We then need to solve it, and then we have to find out how many seconds it will take until the tank is empty. So the tank being empty is going to be when the height of the fluid equals 0, because there's no fluid in the tank. And the question is, what would the time be when that happens? So I've just put under here a diagram. Diagrams always help. This particular diagram is out of the textbook, so it's a nicer looking one than I could draw. And you can see here you've got the height and also the diameter of the tank shown. And you can see the surface area here is a meters squared. Now we know that the radius of this tank is 0.4 meters. So 0.4 meters. So that means the surface area of the top of the fluid would be pi times the radius squared, and the radius is 0.4. So 0.4 squared is 0.16. So it would be pi times 0.16. So that would be our surface area in meters squared. So now what we can do is substitute what we know into our differential equation here. We actually know what k is. K is 0.025. I'll just highlight these in yellow. We know that. And we know a. So we can put k and a into our differential equation. So we've got dH dt equals negative k, which is 0.025, times the square root of h, over a, which is 0.16 times pi. And that is going to be our differential equation. All right. If you wanted to, you might like to do that in a sort of better way instead of using decimals like that. So I'll put that into the cas. So it's 0.025 on 0.16. And to make that into a fraction, I'm just going to go into menu, number, approximate to fraction, and push enter. So 5 over 32. So this is the same as negative 5 root h on 32 pi. So it's just kind of neater than taking decimals around with you. So if you can, turn things into whole numbers, or whole numbers in a fraction this way rather than working with it that way. All right. So the next thing we're going to do, we've actually found the differential equation. Now we have to solve it. So what we're going to do, I'm going to take the dt over to the right side. So we've got negative 5 root h on 32 pi dt. And then I'm going to take the root h underneath, so it's over on this side. So we've now got minus 5 on 32 pi dt. Now what we're going to do is integrate both sides. So from this place we're now solving. And if we integrate both sides, I'm going to rewrite this as, instead of being a denominator as a square root, it's h to the power of negative a half dh. And all of this stuff, negative 5 on 32 pi, that's all just a constant. And we're going to integrate that side too. Integrating here, we get h, add 1 to the power, it becomes a half, divide by the new power. On this side, all of the constant stuff becomes a coefficient of t, plus a constant. And now what we'll do is just take that over to the next page. Oops. So the half is going to flip up and become 2h, and this is going to be the square root of h. equals negative 5 on 32 pi t plus c. Now because we were looking at dh dt, let's solve this now for h. So we're going to solve for h. So we've got divide everything on this side by 2. So negative 5t on 2. So divide the bottom by 2. Divide that c by 2. So we've got square root of h. This is going to be 64 pi. And I'm going to relabel this. I'm just going to call this, I won't use k, I'll use another thing. We'll call it m. So make sure that if you do any relabeling of constants, make sure you say what they are. So I've just relabeled c over 2 as m. Now, take the square root to the other side. So we end up with a squaring of everything on this side. And that's going to be our general solution because we've got our constant still in there. Alright, so this is the first level of solution, and it's a nice idea. I'm just going to write here. This is the general solution. Now we know a bit of information from our question. We know that the tank was initially full, which meant that when t equaled 0, the height of the fluid inside was 1.6 meters tall. So we know that when t equals 0, h equals 1.6 meters. So let's substitute that in to our differential solution, our differential equation solution. So t equals 0, that will be m squared. It'll be 0 all here plus m squared, which means that m equals plus or minus the square root of 1.6. All right. And here, what we'll do is now solve. Square root of 1.6 1.26, and we'll see if we can get a fraction answer for that. Nah, it's quite ugly, so we'll just go with it estimated. So square root, I might keep it actually a square root of 1.6. So I'm going to go with the positive case. So I'm just going to state that the m that I'm using here is positive, so I'm only considering one case. So the other condition that we know, or that we're trying to solve, is what happens when the tank is empty. Okay, so what happens when the height of the fluid is 0? So that's when the tank is empty. So I've got h equals, I'm just going to rewrite this now with my newfound m in there. So when is the tank empty? i.e. when h equals 0. What does t equal? So what we can do is substitute 0 in there, and we've now got negative 5t over 64 pi plus square root of 1.6. Now it's all squared, but because this left side is 0, if we take the square root of both sides, we get to this point, which means we're now looking at solving for t. So take the square root of 1.6 to the left, multiply that by 64 pi, bring that up, and then divide by negative 5. That will be t. And I think in the question here, it doesn't say whether it has to be exact or approximate, but this will end up being an approximate. So we can substitute it all into our CAS. So negative the square root of 1.6. Oops. Negative square root of 1.6. And just going back, times 64 pi on negative 5 times 64 pi, and all of that on negative 5. And see if we can, get an exact answer. I'm pretty sure we won't because of the surd. Oh, it's quite ugly. So we'll just leave it in this form. So, well, it's probably enough really to do this to one decimal place. So 50.8651. Let's round it to one decimal place. So our final answer, we end up with T equals approximately 50.9. And remember the units that we're using here. Have a look back and identify what we're using. Seconds was our T. So it's going to take 50.9 seconds for this tank to be empty. So that's for the height in the tank to be 0. So the amazing thing here is you've actually constructed a differential equation to model the rate of change of the volume of the fluid in that tank, and then you're able to use that differential equation that you've got here to solve it. So there's our solved general solution, and then using the condition that it was initially full, so when t equals 0 it was full to the brim, you could then find by substitution when the tank is empty, when h is 0, what the time is at that point. So a really fantastic example of how you can use differential equations to model real world situations.